So with the Schrodinger equation in hand, what we can do is solve that, and you'll be doing simplified versions of that in your physical chemistry course, but not here. We're just going to look at the results. What you're able to do is figure out that the atomic wave functions are quantized, and that these have a set of quantum numbers. Okay, and these hopefully are very familiar to you from general chemistry courses, right? There's four quantum numbers that have discrete values, um, and we give them special names. Principal quantum number is given the symbol n. That's basically corresponds to the row on the periodic table. Angular momentum quantum number given the symbol L, that corresponds to the shape of the atomic orbital. So an s orbital is 0, L equals 0, p orbital is 1, d orbital is L equals 2, f orbital is L equals 3. And then within that, there's the magnetic quantum number given the symbol m sub L. This ranges from whatever L is, the negative of that, to the positive of that, a 0 in between, again in integers. Okay, this tells you something about the shape of the quantum, of the orbital, atomic orbital. And then there's a spin quantum number, usually we call this spin up, spin down. M sub s is the symbol, and we give it values of +1/2 and -1/2. So just quickly for practice, what are the quantum numbers possible for a 3D orbital or 3D shell? Well, the fact that it has a 3 in there, that tells you it's in the third row of the periodic table. That's n equals 3. D means, remember, S, P, D, so that's L equals 2. And then because L equals 2, that means that M sub L can range from the negative of that to the positive of that. So -2, -1, 0, 1, or 2, those are all valid quantum numbers. And there's going to be, that gives you the 5 shapes of the d orbitals, right? There's 5 numbers there. And then for each of those d orbitals, 2 electrons can go in there, spin up and spin down. So those give ms of -1/2 and +1/2. So in total, we know that the 5 d orbitals can hold 10 electrons, and that's because there's 10 unique quantum numbers. Remember, the Pauli exclusion principle tells us that each electron has to have its own unique set of quantum numbers. So there's going to be 10 sets of quantum numbers that are going to be unique. That can be in these 5 3D orbitals, right? One of them could be 3, 2, -2, -1/2. The next one could be 3, 2, -2, +1/2. And you could go through this, right? Last one, if we went through in this pattern, would be 3, +2, +1/2. Okay. So now what you can do from the Schrodinger's equation is make these probability distribution maps of where the electron is most likely to be. And, so for L equals 0, those are the s orbitals. We tend to think of those as just sort of spheres. That's true for the 1s orbital. You can see there's a certain sign for this wave function, and it just is a sphere, okay? And it's a relatively small sphere. But for the 2s and 3s orbitals, that's a little more complicated. The sign actually of the wave function oscillates. So you can see there's a larger a wave function of opposite sign, but then the interior it switches signs. So that means that because you went from a positive value, let's say, to a negative value, the colors are arbitrary. It could be negative to positive. But because you went from a positive value of the wave function, the solution to the wave function, the probability, right, psi squared, to a negative value, switch signs, you have to go through 0. And so what that tells you is that if you've gone through 0, there is a node. And a node means an area where there's 0 probability for an electron to be found there. So although we don't know exactly where any electrons would be at any given time because of the Heisenberg uncertainty principle, what we can say for certain is that there are certain areas in these orbitals where there will never be an electron there. So that's kind of interesting. You can see the 3s then oscillates twice. So because the shape of these nodes are spheres themselves, we call them radial nodes, okay? So the 1s has 0 radial nodes, the 2s orbital has 1 radial node right in here, And the 3s has 2 radial nodes, one in there and a second one in there. Okay, and 3s is obviously bigger than 2s and bigger than 1s. And it's going to keep going in that pattern. The 4s is going to have 3 radial nodes as we go down the periodic table. Here's sort of looking at the radial distribution functions, okay, of these orbitals. So you can see the 1s, there's some probability close to the center of the atom, okay, so 0 here, not at the nucleus, you're never going to find the electrons, but close to it, right, because 1s is very small. You have a high probability of finding it, and then it tapers off, okay, and it just tapers off. Now you can see for the 2s, look what happens. There's a switch in sign, right? It actually goes negative. This is actually the wave function. It's not the probability. Probability shown down here. That's when you kind of square it, okay? And that's, you know, right there's a node, and then there's another, and then it's going to taper off as you get farther and farther away. For the 3s, you can see there's a node here, right? Switches, and then it switches back. There's a node there. Those are your 2 nodes. So this is looking at one angle and just projecting out, okay, away from the nucleus. If you look at chi-square, the probability distribution, hopefully this makes sense to you. You can see that for the 1s, you know, there's some peak probability of where you're going to find it. You know, somewhere around here. Remember, this is a 90% probability map, so maybe somewhere around there is like the peak probability. But if you get too close to the nucleus, there's going to be 0 probability. And if you get too far away, effectively, there's 0 probability as well. With the 2s, it's a little more interesting because you have that node. There's actually a spike. There's a little bit higher probability, sort of where the 1s is, okay? But then further away from the 1s is really where there's a lot of probability, okay? And so there's some probability to actually find an electron in the core, in more core-like electron, even though you're in a 2s, okay? It has some 1s character. And you can say the 3s too, it also has some 1s character, a little bit of 2s character, but mostly it's 3s character. And that corresponds to the 2 nodes. You can see there's a node here, node there, right? That's there and there. So what else? You can keep going, right? And you can, the Schrodinger equation, you can look these up online. And again, in your physical chemistry class, you'll go into this in more detail, but you can actually see what these solutions look like, and you can look at the mathematical functions. For us, you know, that's a little bit too detailed. We just like to look at the pictures, but the p orbitals, as you know, are dumbbell shaped, and they're going to have another type of node. Okay, they're going to have what we call the angular node, and in one direction, there's 3 p orbitals now, because you can have m sub l be -1, 0, or +1. And depending upon the orientation of these dumbbells, that angular node is going to be in a different spot. So in the px orbital, there's going to be an angular node in the yz plane. Okay. In the py orbital, there's going to be a node in the xz plane. And I could have drawn these, probably should have, with different colors to show that the sign of the wave function is changing from positive to negative or negative to positive. And that in between there's going to be a node. Okay. The z orbital, again, is going to have a node in the xy plane where there's a change in sign. Now, when you go down the periodic table, so this 2p is sort of the first p orbital that you can get, right? The smallest p orbital. You can't have a 1p orbital. If you look at the quantum number rules, you can't have a 1p orbital. So 2p is the smallest that you can get, so it doesn't have any radial nodes. 3p will look like just a bigger 2p orbital, but it will have a radial node. Okay, in addition to the one angular mode that kind of defines a p orbital. So you can see what that looks like in there. There's sort of this mini core-like p orbital with opposite signs as compared to sort of the main outer p orbital. 4p orbital would have 2 radial nodes and 1 angular node. So this trend would continue going to 5p, okay, etc. So hopefully you're seeing sort of a pattern here. What it's telling us is, right, a node is where probability of finding an electron is 0. The number of angular nodes is going to be equal to L, right? So s orbitals don't have any angular nodes. They have L equals 0. P orbitals have L equals 1. They have 1 angular node. Radial nodes is going to be n minus L minus 1. So consider, for example, a 3s orbital, which we went over, right? 3s orbital had 2 radial nodes. Well, 3n is 3 there for 3s, L is 0, so 3 minus 1 is 2, okay? Or what about the 3p, right? 3p had 1 angular mode, so that would be 3 minus 1 minus 1 equals 1. So that's how that works. But you can memorize that formula if you want, or just kind of look at the patterns. I find the formula a little confusing. I just look at the patterns. D orbitals, L equals 2. So M sub L is going -2, -1, 0, 1, and 2. So there's 5 different shapes. Here they are: x, y, x, z, y, z, x squared minus y squared, and dz squared. Do you need to know the shapes of the d orbitals? Yes, I expect you to know the shapes of s, p, and d orbitals. You know, the f orbitals are a little more complicated, but definitely these. We'll be using this a lot. You know, inorganic chemists do a lot of work with transition metals. So later in the course, we'll be talking a lot about d orbitals and really looking at these shapes carefully. But what you can see at this point is the x, y, x, z, and y, z, those are all, they're all related. All 5 are related, but these 3 are very intuitively related. They're these clover leaf shapes, okay? And the x, y is in the x, y plane, right? And in particular, these 2 lobes, sort of these dumbbells, these 2 sets of dumbbells, are in between the axis. So it bisects, you know, this x and y, this orange lobe. Same thing with the YZ, right? Now it's just oriented differently. It's just rotated 90 degrees, but it's bisecting this YZ axis. XZ, same thing. This orange lobe is bisecting the XZ axis. Okay, x squared minus y squared, all that is taking the XY and rotating it 45 degrees. So now this orange lobe is actually on the x-axis, and this blue lobe, they're no longer bisecting. They got rotated 45 degrees compared to the XY. And now this blue lobe is actually on the y-axis, okay? And what about this z squared? This one looks really funky, right? It's not a clover leaf like the other. This is something, you know, I didn't realize for a long time because nobody told me this, and I never learned it early on when I was taking, you know, general chemistry and inorganic chemistry. But the z squared is actually shorthand notation. The real function is 2z squared minus x squared minus y squared. And what does that do? Well, you can decompose that into z squared minus x squared plus z squared minus y squared. So really what it is it's, you know, you can imagine what a z squared minus an x squared looked like. It would just be a yz rotated 45 degrees. And a z squared minus x squared would be a xz rotated 45 degrees. And a z squared minus y squared would be a yz rotated 45 degrees. So those 2 things I just said are the equivalents of this x squared minus y squared, where it's rotated 45 degrees, but just for the other 2, you know, for the xz and the yz that we didn't rotate yet. And then you're just adding them together. So you're doing a sort of like an average of them. And that ends up giving you this shape. Okay, that's why it's such a funky shape. Now, why do you have to do that? Because quantum numbers in the Schrodinger equation forbid you from having 6 orbitals. We can't just have, you know, x, y, x, z, y, z, x squared minus y squared, z squared minus y squared, and z squared minus x squared. That'd be 6 orbitals. So we only have 5, so one of them has to be this kind of weird combination. Why is it this one? You know, why isn't there dx squared or dy squared? That's just totally arbitrary, right? That's convention. So you could do it that way, but nobody does that, and that'd be really confusing. So lastly, we can go look at, okay, let's say, so those are 3D orbitals. Let's look at the 4Ds. Those are going to have an extra, they're going to have radial nodes, right? N minus L minus 1. So n equals 4, L equals 2 minus 1. That 4 minus 2 minus 1 is 1. So these look very similar. It's the same sort of pattern, but they're bigger and they have these radial nodes. The d orbitals, of course, have 2 angular nodes as well, right? So you can see that in here. One's going to be like going, for xc, it's going to be going through here and going through there, right? Nodal planes, they're showed. F orbitals, L equals 3. Well, that means you have 7 of them because you go -3, -2, -1, 0, 1, 2, and 3, right? Here's what they look like. You know, I don't expect you to know these. This is getting a little bit more complicated, but there's more lobes, right? Because there's 3 angular nodes now. And so these would be the 4 F orbitals. The 5 F orbitals would look similar, but be bigger and also have 1 radial node. G orbitals, have you ever heard of G orbitals? Probably not, because no elements in their ground state have G orbitals, at least not yet. We'd have to get to element 119. The periodic table right now goes to 118. That fills up the 4 Fs and the 5 Fs, okay? And to get to G's, quantum mechanics, you'd have to get, actually, you have to get to 121. Yeah, you'd have to get a little bit higher than 119. But they do exist, okay? And you can go higher than this. L equals 5 would be H orbitals. And they're relevant because you can excite electrons into these higher orbitals. So they can go there for a little bit and do chemistry, right? But we don't usually talk about them. And they're gonna have, you know, even more complicated shapes. There's gonna be 9 of them for the G orbitals, going from -4 to +4.